Astronomy, History, Part 2. Law 2 of Kepler's was the equal area law. Basically, this says that as you orbit a focus, Earth orbiting the Sun, comet orbiting the Sun, anything orbiting the Sun, it's going to go faster the closer it is, and it's going to go faster or slower the further away it is. For instance, when you putt a golf ball and it's going really slowly towards the hole, it hits that hole and it lips and comes right back at you. It spins really fast. Well, little gravity is involved there, but you get the picture. Planets do travel faster when they're closer to the sun. So when you map it out, like in the background there, that same object traveled the same distance along the outer line, or the same time. Took maybe 1 month to go to the outer line in blue and 1 month to the outer line in purple. It just went slower further away from the sun. If you were to map the area, then you would see that it is the same. It's the same area in the purple as it is the blue. And his third law is what we call the harmonic law. It's an equation you need to memorize. It's p squared equals d cubed or a cubed. That's a cubed. But we're going to start with d right now, meaning for distance. But a is the average distance from the sun. Okay? So the orbital period in years is equal to the average distance from the sun in AUs. With Earth, that's easy. 1 year, and we are 1 AU away. 1 squared equals 1 cubed. Hey, it's perfect. Orbits and distances are in harmony. Okay, so he took this, pretty smart cookie, took just off Tycho's observations with the sextant, and of course the math from the Arabs. No telescopes, nothing else. Galileo finally burst on the scene. Galileo, Galileo, Galileo. He's believed to be the first scientist to turn a telescope towards the sky. They had telescopes for years before that on ships to navigate and look at other ships if they're pirates. Arr! But Galileo was the first to take a telescope, point at the skies, make observations, and record them that we have on record. Notable telescope firsts. He observed lunar craters on the moon. Lunar moon. Okay. Yeah, moon is the name of our natural satellite. And mountain ranges were on the moon. Ooh. Before that, they really thought that there were seas. The dark stuff was oceans. That's why they're called mare. He also documented 4 big natural satellites on Jupiter we call the Galilean satellites in honor of Galileo. The Galilean moons. There's Io, Callisto, Europa, and Ganymede. Ganymede is the biggest natural satellite in our solar system. It's huge. Not as big as Earth, but it's huge. He also observed the phases of Venus, and lo and behold, they look like the phases of our moon. It's because Venus goes between us and the sun. So we never see a full Venus. A half Venus is as much as we see. We see a full moon because it's on the outside. So Galileo went on to also, well, based on his observations, a guy named Newton. You know Newton, Sir Isaac Newton? Yeah, gravity guy. He came up with the universal law of gravitation. Basically, the big old crazy nice equation down there basically says the force of gravity is proportional to the 2 masses that are involved. For instance, 2 little astronauts there in that beautiful spaceship, the further they get from Earth, the less attraction gravity has on them. So out in space, we have what we call microgravity. The Earth still holds us in an orbit, but it's not yanking us down as hard. So the r underneath the radius squared is the distance between the 2 masses. Now the mass 1 would be the Earth, mass 2 would be the little astronauts in the little spaceship. And G is simply a gravitational constant. Boom. So basically, you're attracted to each other physically. Okay, physically as in gravitational physically, not because your little brains think you're pretty. The further apart you are, the less attracted you are. But you're more attracted to the Earth because it is so much more massive. It pulls you down tighter. If you get two of you out in space, like those little astronauts out there, and we just set them out in space, perfectly still, 10 feet apart, and we walk away, eventually they're going to gravitate towards each other. Just that each other's gravity is going to pull them to each other. All right, so escape velocity, big term, just basically means the minimum speed or velocity needed to escape the gravitational pull of an object, of Earth, of the moon, whatever. Since the moon is so much smaller, the astronauts could get off the moon with a lot less propulsion or energy needed to get them off there than they did off the Earth, because the Earth is bigger. There's our little astronauts taking off over the Smokies. Kepler's third law was then modified based upon Newton's law of gravity, which says p squared equals 4 pi squared divided by k squared times the mass of the sun plus the mass of the earth times a cubed. So this is how astronauts now can determine the mass of distant objects after finding their orbital period. You're wondering, how do we know the mass of that stuff? Okay, you're also wondering, do I have to know how to use this equation? This is high school. We're going to keep it simple. We're going to go p squared equals a cubed, and that's good enough for now. So again, the major axis is the longest distance between 2 points in the elliptic, the orbit. The semi-major axis is the foci, or sorry, the average distance or half of the major axis. So the semi-major axis, A, is the average distance away from the focal point. So A is your semi-major axis. Oops, right there. A is the semi-major axis or average distance away from the planet. Perihelion again is the closest point. Aphelion is the furthest point from the sun. So the focus I put in parentheses is the sun on the left. So p squared equals a cubed, knowing that a is your semi-major axis or average distance a planet is away from the sun for our purposes. The major axis is basically the perihelion plus the aphelion. So how do we figure out the semi-major axis? We add the two together and divide by 2 and get your average, right? Semi-major plus is the major axis plus, perihelion plus aphelion divided by 2. And there we have it again. Since the sun is at one foci, focus, if a rogue asteroid, that's just crazy asteroid out there on its own, is at perihelion Earth's distance away, 1 AU, and its aphelion is 11 AUs away, what is its average distance? So first we take our 1 AU, our closest approach, plus our 11 AU, our furthest approach, add them up, divide by 2. So we add them up, divide by 2, and the average distance away, or the semi-major axis, would be 6 AU. Now we can find out how long this thing's going to take to orbit and come back to see it again. So we plug it in. P squared equals a cubed. So A, we found it as 6 AUs. 6 times 6 is 36, times 6 is 216. We take the square root of both sides to get P by itself. And P now equals 14.6 years to orbit. Yeah, we don't know of any little rogue asteroids that short of orbit, but there are a bunch of asteroids in the asteroid belt, which is kind of hang in the belt. What's eccentricity then? Some things that's eccentric. Let me put it to you this way in format. The further away the foci are, or the more elliptical, the more ovoid the ellipse is, the further from a circle it is, the more eccentric it is. The closer to 0, the less eccentric. So the more perfect circular orbit has basically no eccentricity. So eccentricity is the distance away from a perfect circle. So orbital eccentricity is the amount by which its orbit deviates from a perfect circle. That's your Webster's Dictionary definition. Oh, look, that little smiley face. He's not eccentric at all. He's got a perfect circle, maybe. Eccentricity is equal to the aphelion minus the perihelion divided by the average. So if a perfect circle, your aphelion and perihelion would be equal, then 5 minus 5 is 0. Divided by anything is still 0. So know this equation. Aphelion, the furthest distance away, minus perihelion, the closest distance, divided by the average distance is your eccentricity. If you look at the eccentricities of the Earth and other major planets, you'll find them very, very, very near to 0. That's why naked eye you can't tell that we are eccentric. However, if you measure Earth from the sun during different times of the year, you find, yeah, we do vary in distance. So the higher in eccentricity, the less circular the orbit. How about that moon? All right, if planet P has an aphelion of 60 and approaches Earth at its closest at 40, what's the eccentricity of its orbit? Okay, take aphelion minus the perihelion, divide by the average, which would be 50, you get 0.4. That is very, very eccentric. You will not see any of on the graph, on our chart, none of our planets are that high eccentricity. So here we have Sam on a satellite orbiting the sun. He gets 3 AUs close. He's far away at 5 AUs. How long would it take him to orbit the sun? First, we find the average, right? We take the perihelion plus the aphelion, divide by 2, and that gives us the average. 8 divided by 2 is 4. So take 4 cubed. 4 times 4 is 16. Times 4 is 64. Then take the square root of that, 8 years. Okay. These are all practice for in class, so I'm going to zip on through these. And that's it.